Yeah, so my name is Srikkanth, and uh, yeah, I've been doing computer programming a lot, and then on started CodeChef. Uh, Today I'll be going over the solution or one of the my solution on this problem add-on segments, which is yeah, it's classified medium, but then yeah, even the top code, the highest rated participants weren't able to solve it during the contest. Um, uh, However, today I'll be discussing the solution for this problem. Uh, so prerequisites for this problem are just basic number theory, but uh, yeah, it's not uh, an easy problem at all, which will be seen in the solution. Before we get to the problem, I'd like to inform you about the recent collaboration between an academy and CodeChef, if you were unaware. So, partnering with an academy, CodeChef started a subscription program to teach competitive programming. So, what this subscription gets you is you get taught by uh, the top educators. So these educators are ICPC World Finalists, IOI medalists, and some of them are working currently in a top product-based companies like Google. Yeah, and so they are going to be conducting live sessions for you. Uh, and in these live sessions, you get to interact with them. Like you can ask doubts, and there are TAs who will clarify those doubts for you. Uh, and so these are structured courses in computer programming. So you get knowledge of various topics, and they'll be taught from scratch, from the basics, so that you can understand each concept. And they also have curated practice problems on all the topics that are taught. So you can do those problems, and then you can test your knowledge of what you have learned. And also there are dedicated discussion forums where you can get your doubts clarified by the TAs, etc. And yeah, some of the classes are free right now, so you can just go over there and watch a couple of videos and see how it's like, and judge for yourself if you would like to be a part of this uh, new program. So yeah, make sure to use this coupon code from which you can get the course at the price of $9.99. So that's it about the subscription program. So coming to the problem. Yeah, so the problem statement is simple. So we have so you're given a circular array with n elements. Let's say A1, A2, and so on till AN. So by circular, yeah, it's pretty evident. Like after the nth element, you come back to the first one, and so on. So in this circular array, you can choose. So there are n kinds of operations that you can do on this array, and the ith kind is you can select a subarray. I should say choose a subarray. Yeah, so you can choose a subarray of length I. Choose a subarray of length I, and you can either add or subtract vi from all the elements in that subarray. So so basically you choose B is an element array given to you, and you can choose a subarray of length I, and if you choose a subarray of length I, you are given a particular value that you can either add or subtract from, which is bi. And the goal is to make all the elements 0. Okay, so you want to convert this array to n0 by applying these operations. And you can apply any kind of operation any number of times you want. So there's no restriction on the number of operations that you have or that you're allowed to do. And yeah, this is basically the problem. So yeah, some prerequisites for this problem would be just basic number theory. But yeah, so given this kind of problem statement, how would one go about solving it? Like, what's the first step? So sometimes in these kind of problems, like you would these are like constructive type of problems, right, where the operations are specific. And yeah, you need to find out what, so you're given n kinds of operations, so we need to find out what operations are good or what kind of operations we can do to get the desired result. So usually in these kind of problems, you would kind of look for, some kind of a greedy approach where one kind of operation is more useful than others or something like that. But in this problem, that's not the case. So the best way to proceed would be to mathematically define what happens to the array after a few operations, and see where we can go from there. So immediately you can see that once you choose a subarray of length I, so there are n possible subarrays of length I. So starting from A1, you can have a length I. So starting from any element, you can have a subarray of length I, which will be different. So you have like n different possibilities, and you can choose a particular subarray how many ever times you want, and you can choose whether to add bi or subtract bi in each operation. So an alternate way to put it would be to choose a subarray of length I and add x into bi, or just add a multiple of bi. So it's equivalent. Like either you add x times or subtract x times, or just add a multiple of bi, an integer multiple of bi, so positive or negative. And yeah, so that's so once we have established it like that, then we can say for each subarray, we can consider each subarray and each possible subarray, and we can assign this as a variable. Okay, so let's formulate it properly. So let's say that for a subarray starting from AI of length j, we choose to add the xij multiple of bj. So here, indirectly, what I'm considering is I'm considering all possible ways of all possible operations. So xij could be any integer, like any integer that you can think of. So so once I consider this, so what would be my final array? So if I apply xij, if I apply the operation xij times on the subarray starting from I of length j, basically what this means is I'm considering the subarray AI plus 1, and so on till AJ. And for uh, everyone here, I'm adding Xij into BJ. Okay, so I'm adding Xij BJ for everyone here. Okay, so now once I've set this up mathematically like this, what would be or how to model the final value of uh, every element in the array. So an immediate difficulty here is that this is circular, right? So this J could be so you could have n somewhere in between here, and you could end up with like say A1 or so. Okay, so for a particular element, how to answer or how to deal with the question of uh, which multiples of which kind of operation is being done on it. Okay, so for that, uh, what we can do is let me define another variable. So let me define another variable. Let me define another variable Yij. Okay, so Yij would be the multiple of Bj. The I'll just put an X here. So the multiple of Bj added to AI. Okay. So now we need to relate these Yij with the Xij's that we had. Okay. So this should be simple. Xij. Yeah. So Yij would be equal to Xij plus Xi minus 1j plus and so on till X I minus j plus 1. So essentially what I'm doing here is that so Xij is a number of multiples of Bj that I'm adding for the subarray starting from I. So Bj will come up in all the choices of subarray starting from I minus 1, and so on till starting from I minus j plus 1. So if you consider I minus j plus 1, I minus j plus 2, and so on up until I. So this subarray has length j, right? So for all subarrays starting from I minus 1, and so on till starting from I minus j plus 1, all these subarrays will contribute to the net value added at AI by subarrays of length j. Okay, so if so once you formulated it like this, So essentially here, what I would like to do is I would like to choose Yij instead of Xij. So that will become clear the following slide. So if you, with this definition of Yij, the final value of AI can be written as AI plus sigma Yij Bj. So this is a simple formula, right? Like this is much easier to deal with than the circular summary. So once we, so this will help you in uh, breaking down the problem for you. So yeah, so once we've defined it like this, yeah, so this is the final value of AI, and we would like this to be 0. We would like this to be uh, 0 for all I. So that's the goal. So immediately when you look at this equation, right? So this is not like this is what we call linear Diophantine equation. So here all these variables AI, Yij, and Bj, they are all integers. Uh, let me. Yeah, so these values, they're all integers. So unlike a no, like a usual equation that you would have dealt with, where the values are all real numbers, here the values are restricted to integers. So these kind of equations tend to be more difficult to solve because of the additional constraint that they have to be integers, right? So we can't freely choose whatever value of Yij we want. So here I would like to recap some theory. So yeah, uh, yeah. So in this equation, linear Diophantine equation. So we'll see how to solve that if you didn't know already. So before that, before I move forward, I would like to just ask if you had any questions up to what was discussed now, because like this is the starting point of the solution. Like yeah, things get, everything is based out of this formulation. Like my solution is based out of this formulation, like starting from here. So if you had any doubts, you can ask in the chats. Uh, so that I can get to those questions. Cool. Right. So, in case you were not aware of how to solve Diophantine equations, we just go over the theory of it. So, if you have an equation ax plus by equal to c, where ax, by, c, they're all integers. So this, so a and b are values given to you, and x and y are the variables which you want to solve. So this particular equation will have a solution only if c is divisible by GCD of A comma. Okay. yeah, so GCD is the greatest common divisor. So since the greatest common divisor of A and B obviously divides A and divides B, so the left hand side is divisible by the GCD. So yeah, it's an equation. So if the left hand side is divisible by GCD, obviously the right hand side is divisible by GCD as well. But so that is kind of obvious. But the unobvious part is that this is sufficient. So as long as the left hand side and the right, as long as C is divisible by the GCD of A comma B, you can always find integers X comma Y which satisfy this property. And so why is that the case? So we can show that that is true by constructing an algorithm that gives you the value of X comma Y. So in this case, Euclid's GCD algorithm does this exact same thing for you. So yeah, so I would encourage you to look up Euclid's GCD algorithm. So if you remember the algorithm, so if you write A as BQ plus R, like dividing A by R, Q is the quotient and R is the remainder. And if you keep doing this until R is 0, eventually like divide A by B, then divide B by R, and so on. Eventually, you will get the GCD here, and you can retrace those steps to get this X comma 1. So it's kind of well known. So I would just like recap this quickly because that's what we've been using here. So this is for two variables, right? So what if we had more than two variables? What if we had, which is exactly what we have here, right? Yeah, we have like so many variables, n plus 1 variables here. Similar to, yeah, here we have only two variables, here we have multiple variables. So how to deal with it? So you can view this as this summation equals minus AI. So essentially the same thing that we are trying to solve, but not quite. We'll get to that later. But yeah, so essentially the same thing. So how to extend this for multiple variables? So that's pretty easy. So if you had more variables, right? CZ. Okay, so let's say CZ equals E. So if you had more variables, what you would do is you would reduce this to variables. So consider this guy. So we know that this guy must be divisible by the GCD of A comma B. So we can replace this by GCD of A comma B into, let's say, Z dash plus C times C equals to. So I know that I can replace it like this because I know this will always have a solution. So I have reduced this equation of size 3 to an equation of size 4. Sorry, equation of size 2. And now I know that yeah, apply the same thing again here. So there will be a solution here if D divides the GCD of A comma B and GCD of C. So yeah, this will have a solution whenever D is divisible by the GCD of A, B, and C. Okay, and again, similar thing. That's obvious because left hand side is divisible by GCD, so right hand side must be. But it's more importantly, we know that there will exist a solution because of the construction. So that's not too obvious. So you can see like the pattern that's being we had an equation, right? And we considered because they were integers, we considered the left hand side saw what it was divisible by and said that the right hand side would be divisible by the same thing. So that gave us a necessary condition that C must be divisible by C. So that's a necessary condition. But that was also sufficient because we had an algorithm which constructed the solution from the necessary conditions. So the necessary conditions were also shown to be sufficient. So which is exactly what we're going to do here, but in a different flavor. because uh, because of this additional equation, this will cause some problems for us later. Yeah, but for now, yeah, it's clear that uh, that AI should be divisible by the GCD of BJ. So that's just one constraint. But unfortunately, that's not sufficient. Like that's a simple constraint, but that's not sufficient for this problem. Why is that not sufficient? Because here we don't have the freedom of choosing any integers we want. So what I mean by that is suppose you found a solution to this equation, right, with some values of yij, you need to be guaranteed that xij values also exist and they are also integers, which is uh, which is not so obvious, right? Because yeah, I can have a set of yij, but I can also have a case where there does not exist integers xij that satisfy my choice of yij that I would have wanted. So yeah, so let's see how to find. So suppose we had a set of choices for yij, how to find these xij's. So that's something that we look into. So here, how many equations we have? We have, so let's say yij's values are fixed. So here we can vary I from 1 to n. So we have n equations and n unknowns, namely x1j, x2j, and model xnj. Note that because of the fact that it's circular, uh, there are n variables and n equations. Uh, and yeah, typically how you would solve linear simultaneous equations. So we can adopt the same thing here. So we can write this in matrix. So if we do that, what we get is right. So a circular array of size j then followed by zeros n minus 2 zeros, and you have x of j, x of j, x of j being equal to y1, y1j, yn. So this is standard matrix representation of simultaneous linear equations, right? So this would be circular. So by shifting this by 1 in each row, you will get the n by n matrix here. And yeah, so the typical way to solve this is take the inverse of this. So if I knew yij's, I would just take the inverse of this matrix, multiply it here, and get values for x1 to xn. Of course, like you know the theory, right? So this matrix should have a non-zero determinant, then this works. But if it doesn't have a non-zero, so what we want is we firstly want a solution to exist. That's the first criterion. Of course, we need a solution to exist. But another important constraint is that xi's should be integer. Okay, I'll write it like this: belongs to z. Yeah. So in addition, it's not sufficient if these yi's are integers. We want x to be integers as well. So you can imagine that the inverse of this matrix will have fractions and etc. So we still have to. So there are constraints on these values as well. So I have to choose values for yij in such a manner that these x all these guys turn out to be integers in the end. Okay. So yeah, at this point, what I'd like to do is okay. So this is a specific type of matrix, right? Ones are occurring, so there are same number of ones in every row, and they are in a circular shifted fashion. So you could, if you actually try finding out the inverse for some of these matrices, you can find a pattern. But that's not the direction which I'll go in. Instead, what I will do is right. So firstly, for a solution to exist, right, we want the rank of this matrix to be strictly should be less than or equal to the rank of the equation matrix. Like uh, if you add yij's here in a separate column, that matrix should have a strictly a higher or equal to rank. That's one way to go about arguing for solutions to exist. But here, what I'm going to do is I'm just going to find out some constraints, and I use the fact that in fact that these rows are cyclic shifts of consecutive ones. So this is I know it makes sense to do this if you look at the left hand side. So what I'm going to do, so here I would like to recap something called row transformations. So yeah, so if you do some row transformations in this matrix, matrix multiplication follows this nice rule that if you have A, B equal to C, and if you do some row transformations on A, the same row transformation will be carried out on C as well. So here I'm going to simplify this matrix by consider any common divisor of n and j. If you consider any common divisor of n and j, and you start from row 1, go to, let's say the common divisor is d. Okay. So common divisor of n comma j is d. So what I'm going to do is take row 1, take row 1 plus d, 1 plus 2d, and so on. So because d is a factor of n, eventually you will come back to 1. So just consider just before that. So just before coming back to 1 again, you will have had some value. So that would be n minus d, I think. N minus d plus 1. Yeah. So consider these values and do the row transformation. R1 equals R1 plus t. So what's happening here? So if you visualize these elements, sorry, the ones in each column, in each row, in each of these rows, so they are shifted by a unit of d. Right? So this one in the next row that we consider, that is 1 plus d, will be shifted by d. Then it will be shifted by d again, and so on. So if you add up all these rows, what you would get is you would get a uniform array. You would get this guy. You would get you would get the same value for all elements. So it would be something like X, 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 X. If you do this row transformation. Why is that so? Because yeah, you can imagine that it's a cyclic order. So all operations being done on every row is symmetric. So it's not hard to figure out that all these all these guys will be equal, and because they'll be equal, we can easily figure out uh, what value they'll have. So they'll have a total of so how many total ones you have? You have a total of j into d ones, and that's divided into n possible values. You have j d by n. So this value will be j. Okay. So yeah. So sorry, I think I'm the number of rows that you had is n by d. So you have 1 plus d and so on till say plus minus 1 into d or so these are equal, and add the n by d. So you have n by d rows, and you have a total of n by d into j. Yeah, so you have a total of n by d into j ones split across n guys. So you have a total of j by d, x equal to j by d. So yeah, by doing this row operations, what we managed to do, so we added the first one plus d, 1 plus 2d, and so on. So we added all those rows up to the first guy. So if we do that row operation in this matrix, we have to do it in this matrix also to be consistent. So if we do that, yeah, so we can do that for 1 plus d, 1 plus 2d. Similarly, we can do it for 2 plus d, 2 plus 2d, and so on. So essentially what we'll have is we'll have the first d rows to be all having x attribute. What we have is j by d, and so on for d rows, and then we have some yeah, we have the untouched rows here, the d plus 1 to n rows, and here we have y1 plus y1 plus d, 1, y2 plus y2 plus d. Yeah, so on till yd plus y2d, so on. So what we've done is actually quite nice, right? Because what this shows us is we have found Okay, so the rank of this matrix is at least D minus, right? Because we have D rows which are completely equal to each other. So I can make the first D minus 1 rows is 0. Uh, so, so that actually tells you a lot, right? So instead of calculating a determinant or whatever, uh, we use row operations to get this. So what have we shown here? Okay. So we have now got constraints on the variables y. Okay, what are the constraints? So yeah, remember the matrix X was here. So let's just multiply out the first row, right? The first row, the first column, if you multiply, you get j by d uh, into this guy plus j by d into this guy. Take j by d common. So you get j by d into some of these values equals this guy. Okay, so what that tells you? That tells you that y1 plus d plus y1 plus 2d plus and so on uh, up until you reach uh, n plus 1 minus d. Uh, let me just write it explicitly. Okay, this is equal to j by d into some integer. That integer is the sum of the xi's here, but I'll just call it capital Y, uh, capital Y, D, let's say, or I think J is more. Yeah, so this is some variable that I want to just have. So I'm just writing it as yj. Right. So another thing that tells you is that the first D rows of this product is the same, right? Because uh, the first D rows are the same. So obviously this row into this column will be same for the first D rows. And so all these guys are equivalent. So y so y1 plus d plus y1 plus 2d is not y1 plus 2d, and y replaces by 2 and so on till d. So all those guys, they are equivalent to this value j by d times yj. That's why I had this convenient value yj here. Okay, so we've now got like some useful information, right? In addition to the fact that the GCD of PJ must be AI, I must also look for solutions where this satisfies. Okay, so the integers cannot be any value I like or like here. So if I could freely choose x and y like I did here, the GCD constraint would have been enough. But here I have this additional constraint that must be satisfied, and that makes problem a bit harder. Cool. So now we have like more equations. So we have one diagonal and an equation here, but with subject to constraints as well. So yeah, there's no bona fide method for these kind of equations which are restricted to integers, right? So you have to be uh, a bit clever in manipulating the equations and all. And you could, I don't know, I think it's possible to deduce this straight from the fact, straight from the problem. Maybe if you were, if you think about it a little bit, but this is, yeah, this is how I, okay, maybe it's a long procedure, but shows you, yeah, from basic principles, right? That this must hold true. It's like kind of a proof for it. So once here, I need a way to deal with these equations. So, or to incorporate them into the solution. And one way I can do that is to, yeah, so remember these are n equations. So you can vary uh, so you can vary I from 1 to n. So this is basically n different equations for all I. Uh, and what I'm going to do is I'm going to uh, so here J was constant. Right. Goes without saying. There's a J, these J's are everywhere. But uh, so one more thing. What value of D should I choose? So the higher value of D I choose, the better my constraint, right? So if D is larger, yeah, obviously I get a lot more elements equal here. And also, like if the fact that uh, these guys are equal for a big D, or let me put it like this: if this thing is value for is true for a larger D, it's true for a smaller D as well. You can kind of work that out. So yeah, so remember we started out with D as being a common divisor of n and j. So since I'd like D to be as large as possible, so we choose D equal to GCD n comma j. Right. So this is one equation to satisfy that y1 plus d and y1 plus 2d, these partial sums, they must all be equal. So whether I start with 1 or whether I start with 2 or whether I start with b, etc. And not only must they be equal, they must be divisible by j by d as well. Right. So is this enough? Well, uh, almost, but not quite. Uh, yeah. Once we, even if this is true, we still have to take the inverse and multiply it here, and we need to be ensured that these guys are integers, right? This is kind of like an exercise to be worked out. Like if you observe the pattern, these matrices, right, their inverse will have a fraction of 1 by n. So if the inverse exists, or if you are able to reduce it to a smaller matrix by removing the redundant rows, what you will end up with is you will end up with a matrix whose inverse has fractions in the form 1 by n into something. So, for example, you can try it out for yourself. Versus this guy, for example, 110, 011. This matrix will be something like 1 by 3 times, so there'll be some minus 2's here and 1's. So only minus 2's and 1 will be here. The order kind of uh, messed up here. So I think it starts out with minus 2 here, something like this. I may be wrong here, but yeah, so I recall the matrix is something like this. So yeah, so remember that we have to, yeah, nobody writes this minus 1 here, but yeah, just for convenience sake, yeah, you should never write matrix power minus 1 like this. You can write a power minus 1, but nobody writes this power minus 1. But here, for the sake of convenience, just we'll just allow that. Yeah, so you're multiplying this with y1, y2, y3, and this must be an integer. So every, so this is like y1 minus 2y2 plus y3, y3. So I can rewrite it as y1 plus y2 plus y3 minus y2. Okay, so all rows I can write like this. So this row I can write it as y1 plus y2 plus y3 minus y3. This one I can write as y1 plus y2 plus y3 minus y3. So essentially, if this value is an integer, or if y1 plus y2 plus y3 is divisible by 3, then everything else is needed. So apart from this constraint, yeah, apart from this constraint, what I have is I have sum of yij is divisible by n. Okay, and this is necessary and sufficient. So if these sum of yj's are divisible by n, and you have this constraint, then I can be assured that these x's will turn out to be integers, and that I eventually have a solution. Yeah, but still, yeah. So now we have even more cumbersome equations, but yeah, we'll reduce them to simple constraints in a minute. But I'd like to point out that these two deductions are like very useful. So now we'll look at the first subtask. So a lot of people got the first subtask right. So for the first subtask, all the AIs are equal. Okay, so let's move to this equation. Let's move to this equation. So this term is constant, same in all the equations, but these constants may not be, right? So let's choose one particular equation and suppose that there were variables yij that satisfied this for one particular equation. So what I'm saying is that these values of yij's here, right? So if they if just because the AIs are equal doesn't mean that the yij should be independent of I, right? It need not be, but we'll show here that it is using our conditions here, or maybe it may be obvious to you. but this is like a formal way to prove it. So suppose you have one equation and one set of variables yi j that satisfy the ith equation. Let's make all the yi's equal. So let's consider the case where I use the same values for other equations as well, assuming that I know one particular solution, one particular set of yij's that satisfy one equation, then both these constraints are satisfied. Like, yeah, sigma yij is just yi into n. So y 1j, let's say, into n. Because I said that yij is same for all I, right? So this constraint is satisfied. Similarly, what about this constraint? This constraint is also obviously satisfied because all these guys are equal, right? For a given j, all i's are equal. So all these y's are equal, and so this guy I can rewrite him as so how many variables are here? So the number of variables here is difference plus 1. So there are n by d variables here, right? Remember, d is the GCD of j comma. So there are n by d variables here. So we can write this as y into n by d. And that must be divisible by j. So that's oh, sorry. I guess we have yeah. So you can see that both these constraints are satisfied, and so if there exists a solution, there will exist a solution with all yij's equal independent of that. So once you have that, it's the it becomes easy to solve this. So let's work it out. Right. So remember this partition that the partial sums with intervals b are divisible by j by d times yj. So if you add up also, let's add up all the equations. If we add all the equations up, what we get is so this expression would be repeated d times from 1 to d. So you have j times yj here. N into a1 plus n into j by d. So d here is actually different for each j, right? So dj GCD of n comma j times bj times some xj equals 0. So if we divide by both sides, we get that this guy will have a solution only if sum over all j. Okay, only if A1 is divisible by the GCD of all these guys. So let's go further. So if we define G to be GCD of I into I by GCD of I for all I, a solution exists only if A1 mod G is 0. So that's the first sentence. So I guess, yeah, most contestants guess that, if all AIs are equal, probably all YIJs are equal as well. Or maybe it was intuitive that a solution like this always exists. So once you know that, then yeah, you can get this equation which gives you this condition. And we just saw that if that condition holds, that it is in fact true that there will always exist a solution where all YIJs are equal. So that's the first subtask done. So for the second one, yeah, it's not so easy because we'll have a tough time working out all these constraints into this equation. So at this point, let's consider okay, so let's first try to work this constraint. Okay. That all these guys should be equal independent of D. So yeah, so as I mentioned, right, if this expression is true for D, it is true for any factor of D as well. So you can easily break this down into partial sums of factors of D and add them up. So if it's true for D, it's true for any factor of D as well. So we'll try to sum up these equations to kind of remove the VJs and get like a centralized, and bring together this constraint for different J. So note that D depends on J, right? D is the GCD of n comma J. So let's define something else here. Let's define G1 to be the GCD of this guy, GCD of J comma n for all J such that Bj is greater than 0. Okay, so this is this should be obvious to say but not to consider because it's easy to overlook this. So if there may be some Bj's which are 0, right? So if Bj is 0, that means like I'm not allowed to do those operations, right? So I'm just going to, there's no point in considering Yj values for them. In fact, it would be incorrect to say those Yij's satisfy these constraints because those Yij's can be anything. into bj is 0, doesn't really matter. So consider only those j's such that bj is greater than 0. And let g1 be the GCD of uh, j comma n for all of those indices. So this kind of partial sum over g is satisfied for all such j, right? So let me do this. Subtract equation 1 and equation 2. So let me write it explicitly. A1 plus sigma y1 j to j. Bj is greater than 0. Consider only those guys. So the others are 0 anyways. So they don't matter here. Okay. And A2 plus sigma y j j. Again, bj greater than 0. And just subtract what happens. Subtract, you get A2 minus A1 plus sigma j minus it's 2 j minus j times j. And this guy or summation of this guy from here, from these, from these equations, you can deduce that this guy is going to be a 0. So we need to so we need to incorporate this equation, right? So here I terms are varying by this factor of d. So if it's true for d, it's true for factors of d as well. So I'm considering g to be GCD of all such d's which I care about. And let me add, so you have these different values of I, right? So add all these equations. So that you get y1 plus d1, y1 plus 2d, and so on. So so here you have y2j minus y1j. So we got, we should start with y1. Y1 plus y1d, 1 plus 2d, etc. Right. So, yeah, as we saw, starting from y1 or starting from y2, this expression should be the same, right? So, if we subtract these two, we get this we rewrite this. So add equations 1 for I equal to 1, 1 plus d, 1 plus 2d, etc. And add them for, and then subtract equations I equal to 2, 2 plus d, 2 plus, so I should use g instead. 2 plus g. So if we do this, then what do you get? What you get here is sigma A2 minus A1, or instead of, we just write it out. So A2 minus A1 plus A2 plus D minus A, so I should use G here. A1 plus G plus and so on. So this pattern, if we add, so we get, if we add these equations, this would be one, the sum of all the A terms. What happens to the sum of the other terms, right? Interestingly, they all cancel each other out, because as we saw, right, 1 plus d, 1 plus 2d, etc. So on, if you have, so all these terms, so it should this expression is same if you start with 1 or start with 2. So that's exactly what you have here in the y terms. The y terms, you will have y2 plus g plus y2 plus 2g, so on, minus y1 plus g plus and so on, and summation of this overall g. So this term will cancel out and become 0. So what that tells you is that these terms should add up to 0. A2 minus A1 and A2 plus G minus A1 plus G. That's it. So this must be true for the pair 2, 3 also. So A3 minus A2 plus A3 plus G minus A2 plus G. Everything must be equal to 0. Sum of everything must be equal to 0. So this gives our first condition, that for a valid solution to exist, summation A AI plus 1 G minus AI comma, AI plus this term here. AI plus 1 minus AI. Let me just call this summation. Plus AI plus 1 plus G minus AI plus G and so on. This summation must be 0. So alternatively, what you can say is in the difference array, AI plus 1 minus AI, the sum of all terms which are G terms apart must be equal to 0. So this is the first criteria. We'll get the second criteria by doing the same thing, but modulo P per K, modulo some prime. So as we did here, right? So we considered what factors the left hand side is divisible by, what factors the right hand side is divisible by. I will able to reduce some conditions on etc. So similarly, what we are going to do is we are going to consider the same equation. Consider the same equation, but modulo some prime power k. So or modulo any number even, but if it is, but it's enough if we consider modulo p per k, because we can use the Chinese similar theorem and multiply things together and say it's true for any number. So just let's say we see if the left hand side is divisible by p per k. Obviously, right hand side is 0, right? It's divisible by any number. It's divisible by all p per k. So the left hand side should also be divisible by all p per k. So what we are doing here. So when we are looking for, when we are saying that the left hand side should be divisible by p per k, all the numbers bj's which are divisible by p per k already, right? They can now be regarded as 0. So in our next condition, we will omit out or remove all bj's, consider any prime p and any power k. So remember here, we removed all the bj's which were 0. Here what we would do is consider the same equation, but modulo p per k. Okay, and what will happen then is modulo p per k, some additional j's may be eliminated, even though some bj's are not equal to 0, they may be divisible by p per k. So those bj's we will ignore, and we will get a new g, and we will test whether this expression is 0, or modulo p per k, we'll see if that expression is 0, and that's our second condition. So we need not consider every prime p and every prime p per k, just those p per k that exist in some bj. So prime factorize all the bj's. So if we have p1 for q1, p2 for q2, consider only these numbers. Okay, so consider p1 for p1, p1 square, p1 cube, and so on till p1 for p1. Then consider p2, p2 square, so on till p2 for p2. So how many such numbers you'll have? You'll have very few such numbers, because yeah, I mean, the number of primes, the maximum value of a is 10 power 4, right? So the number of primes you'll have will be even smaller, something like 10 power 4 by ln 10 power 4. And then after 2, the number of powers will decrease like very drastically. So 2 may have like some 10 powers up to 10 power 4, like 13, I guess. 13 powers less than 10 power 4. But after like 10, you have only 4 powers. So that's constant number. So essentially what you will have to do is you'll have to check for O of number of primes less than 10 power 4, let's say. Just a little more than that in terms of space time complexity, but I mean, for this range, we really don't care about. So it will be like very small. Like even 10 power 4 log 10 power 4 is like a good upper bound for that. And then we will have to test it on all such ends, right? So potentially you could have 10 power 4 log 10 power 4 into 10 power 3. So so condition 1 and 2 can be checked, and they are essentially the same, except you're considering modulo p per k. In fact, this is considering modulo some large prime number or k, we can say. So we've got two major conditions out. The third condition is like along the same lines. So we've managed to incorporate one of the constraints, that is the sum of the yi's should be equal, the partial sums of yi's with space d must be equal and divisible by j by d. We've incorporated that. We still haven't incorporated the fact that they must be divisible by j by d, and we haven't incorporated the fact that the sum of yij must be divisible by n. So let's do that. That will give us our last constraint. So one way to do that would be to just sum up all the equations. If you sum up all the equations, you get, let's see what you get. Let's see what we get. So, right. So firstly, the sum of yij's must be divisible by n, right? So what you have here is that j into yj. So if you add this for all possible indices, so you have 3 different terms here. So this term for this particular j would be j into yj. So so you get j to capital yj, and this must be divisible by n. If this is divisible by n, then yj must be divisible by so equivalently jyj by n is an integer. So you can imagine that some factors of n are cancelled out by some factors of j, and the remaining factors must be present in yj. So yj is divisible by n by gcd of n comma j, which we saw was d. So yj must be divisible by n by d. So let me rewrite yj as n by d times zj, let's say. So this will give us this will give us a useful information. So now let's add all the equations. If we add all the equations, you get uh, j into yj, right? So you get, yeah, here we get all the matching numbers. So if we add up all the equations, we get sigma ai plus sigma n by d into j times cj times pj, and this must be equal to 0. So this is like, yeah, this will give us the final condition. Note that this is similar to the one that we had when all the y's were equal, but now it's inconvenient because earlier we had n into a1 and we could just cancel off that n here. But here what we will do instead is we will use it to find these constraints on this sum a1. Uh, Specifically, consider this guy modulo p part. So consider this guy modulo p part k. Again, for some p part k, that's divisible by some p. Okay. Right. So note that um, firstly, let's state the obvious fact that sigma ai is divisible by GCD of n into j by d into bj. So you can take n out here. Yeah, so sigma ai is divisible by n into GCD of j bj by. I should actually add a substitute here. D is the GCD of n comma j. So d depends on j here. But yeah, let's call this GCD overall j, this magic number to be g from here on. So yeah, sigma ai must be divisible by n into g. So that's one fact, and unfortunately that is not enough. So yeah, okay. So yeah, we got this one constraint, but this is not right, unfortunately. So like how we did here, we will consider modulo p per k as well. So if let's say n is, so let's consider those p per k's that are in bj's like we did before. If some n, let's say that n has p power t, or p power t is the highest power of p that divides n, right? So yeah, we can remove all bj's which are already divisible by p per k. For those which are not divisible by p per k, we find out that this expression, right, it will turn out to be divisible by p part if we analyze carefully. So there are cases, right? So if we consider the highest power of p that's present in n, in j, and in d, we can get some bounds on the power of t present here, and we'll find that if the power of p is not present uh, enough in if it's not present in j, it will be compensated by these j by d. So yeah, so our final constraint is that uh, so here we added up the sum for all I, right? So if some bj's are divisible by p per k, we can omit them. So consider only those partial sums of I which are the difference of p per t, where p per t is the highest power of p present in n. And if you consider that and work out the cases, you will find out that this partial sum must be divisible by p per k as well. So there are two possible cases where you consider the highest power of p in j, and then you consider the case where t is less than k and t is greater than k. You'll end up with this nice fact that the partial sums of I with a space of p per t must be divisible by p per k. So that's the final constraint that will happen that we'll have in this problem. So if we so if you guys see the editorial, right? So the editorial doesn't the editorial is a proof that's present in courses right now, but it doesn't really give you an intuition of how to obtain those constraints. So here I hope I gave some insights on how to intuitively find those results. And yeah, so these three conditions are very simple to check, right? So all we have to do is simply brute force this thing. So checking these constraints is not a big deal. The hard part is in coming up with these constraints and arguing that they are in fact sufficient. So first you will have to find out constraints by seeing what terms are divisible by what times. Then you will have to argue that it is sufficient by coming up with the construction of the solution, assuming the constraints. So for the construction, like we see the editorial, it's like concise there, but the editorial doesn't cover this part, which I hope I covered well in this video. So that's it for this. I'll take any questions if you have. So meanwhile, I'd like to find out again, like if you still stuck around, that I'd like to remind you about the subscription program and check it out. Yes, I forgot to tell you about the feedback. So this wasn't like yeah, this was like a really typical problem. So I tried to explain all the basics, and also I hope you get some ideas out of uh, this problem. uh, I was able to convey some ideas to you. Yeah, so please fill the feedback form, and we'll definitely check your feedback out to improve ourselves next time. So don't forget to fill the feedback if you stuck around. And thanks for watching. Yeah, thanks for watching, guys.